Bash script, batch type hint adder across a Python codebase. Welcome to lesson 3.3. By the time this lesson ends, you will understand exactly why naive bash loops for Claude automation fail at scale, and you will have a working, production-grade solution in your hands. This lesson builds on the stdin/stdout piping patterns from lesson 3.2. Here we add 3 critical capabilities that separate a toy script from a production tool: idempotency through SHA-256 file hashing, error resilience through explicit exit code handling, and resource awareness through token budget conscious batching. The artifact you build today, batch_type_hints.sh plus its JSON state file, can be dropped into any Python project and run as a scheduled CI job. It maintains its own progress log, skips already processed files without reinvoking Claude, and continues gracefully when individual files fail. Engineering teams that skip this architecture burn money. A 200-file codebase with a naive loop that crashes on file 150 means reprocessing all 200 files on restart. At roughly 2 cents per file, that is $4 wasted. But in a 50,000-file enterprise codebase, it becomes a real budget line item. More critically, it produces duplicate diffs that require manual review before merging. Have you ever had a script fail halfway through a batch operation and had no idea where to resume? That problem disappears today. Let us start with the exact code pattern that trips up almost everyone new to headless Claude automation. What most developers write when they first discover Claude dative P. This is the code you will find in most tutorials and Stack Overflow answers about automating Claude. It looks reasonable until you actually run it in production. The loop is straightforward. Iterate over all Python files in src/ call Claude-P with the file contents, redirect the output to a dot-typed file. If you have tested this on 5 files, it probably worked beautifully. Let us walk through each failure mode so you understand exactly why they occur. Token waste. Every time this script runs, it processes every file from scratch. If it crashes on file 50 of 200, you restart and process files 1 through 49 again. Those tokens are gone. There is no mechanism to remember what has already been done. Duplicate diffs. Claude is non-deterministic. Running the same file through the same prompt twice often produces slightly different type hints, especially for complex function signatures. Now you have 2 conflicting versions to reconcile manually before you can merge. Silent exit failures. When Claude-P encounters a rate limit, authentication error, or network timeout, it exits with code 1. A bare bash for loop does not check the exit code and happily continues, storing whatever partial or empty output exists in the dot-typed file. You will not discover this until you try to use that file. ANSI code corruption. By default, Claude CLI outputs terminal color codes, escape sequences like \033 32 meters. If you pipe that output into a JSON parser or into JQ, it crashes immediately with an invalid JSON error, because those escape sequences are not valid JSON characters. No resume capability. After a crash, you have no record of which files succeeded and which failed. You are back to square one with no choice but to restart the entire batch. One network hiccup or prompt typo means reprocessing the entire codebase, burning tokens, and generating conflicting diffs on every file. Our solution is a stateful batch processor with file hash tracking, exit code handling, and token budget awareness. Let us understand each failure in more technical depth before we build that solution. Why each one occurs under the hood, and how to detect it in production. Let us get technical. Each failure has a specific cause and a specific fix. Context window overflow. Globbing all files concatenates them into one massive string, easily hitting 75,000 tokens. Claude silently truncates the earliest files with no warning. Fix. Batch 5 files at a time. Reprocessing burns tokens. No state file means every restart loops from file 1, generating different diffs for already touched files. Fix. SHA-256 hash in a JSON state file. Skip if the hash matches. Non-zero exits are silent. Claude-P exits with code 1 on rate limits or auth failures. A bare loop ignores this and commits whatever partial output exists. Fix. Set ewo pipe fail plus an explicit if not check on every Claude call. ANSI escape code corruption. Claude CLI embeds terminal color codes in output. Piping that into JQ or JSON.parse crashes immediately. Fix. Prefix with no_color equals 1, or strip codes with sed. No token budget visibility. You cannot ask Claude how many tokens remain. You discover quota exceeded only after a mid-batch failure. Fix: query Claude/status before each batch segment. Exit code failures are the sneakiest. The script finishes with exit code 0, but your .typed files contain error messages instead of Python code. You only find out when py_compile runs. Let us look at the architecture that fixes all 5 at once. How each component connects to deliver idempotent, resumable automation. This diagram shows all 5 components of the CloudForge batch processor and how they connect. Every element here corresponds to a real file or subprocess call in the final script. The main flow runs left to right across the top row. Python source files from src/*.py are fed to the batch processor, the shell script we build in this lesson. The processor calls Claude CLI one batch at a time, and the output flows through a syntax validator before being committed as the final typed Python files. Below the main flow are 4 supporting data stores, each solving one of our 5 failure modes. The state file stores SHA-256 hashes of every processed file, enabling idempotency. If you have already seen this exact file, skip it with 0 tokens consumed. CLAUDE.md is read by Claude at the start of every session. It carries your project conventions, the Python version you are targeting, and which type hint style to use. The syntax validator intercepts broken output before it can corrupt your codebase. The error log captures stderr from every failed Claude invocation, so you can diagnose failures without stopping the batch. Notice that observability, the error log, is a first-class component, not an afterthought. What other areas of your automation workflows currently lack proper observability? In production, this architecture lets you run the batch processor as a weekly CI cron job without human supervision. The state file persists between runs, so files added since the last run are processed automatically. Files that were already handled are skipped instantly with 0 API calls. Let us look at how the state file and Claude.md work in detail. These 2 data stores are the heart of what makes this system idempotent. 2 complementary persistence mechanisms that make runs resumable and consistent. The state file and Claude.md are what separate a resilient automation from a fragile script. Let us walk through what each field does and why we store 2 hashes instead of 1. The state file stores 1 JSON entry per processed file. The path field is the key for lookups. The file _hash is a SHA-256 of the original source file's contents. If a developer edits the file after type hints were added, the hash changes and the processor knows to reprocess it on the next run. The diff_hash is the second, less obvious innovation. Once we know a file needs processing, we estimate what diff Claude would produce, and if that diff hash matches what we already applied, we skip the API call entirely. 0 tokens consumed. This is what makes weekly CI runs nearly free. Unchanged files cost nothing. The timestamp lets us implement rolling archives for very large code bases. State entries older than 90 days can be pruned to keep the state file under 10 megabytes. Claude.md is read by Claude at the start of every session. It contains your project's Python version, type hint style conventions, which directories to skip, and a running progress count. This ensures that file number 150 of a batch uses exactly the same conventions as file number 1, even if they are processed weeks apart. The optional T versus T-pipe none choice in Claude.md matters more than it might seem. On Python 3.9, T-pipe none is a syntax error. Without Claude.md enforcing the convention, Claude might use either style across different files, causing CI failures that are painful to debug. What happens if the state file is deleted? The processor simply reprocesses all files on the next run. Expensive in tokens, but never dangerous. The state file is advisory, not authoritative. Now let us look at the actual bash script and how it handles each error condition. This is the core processing loop, the heart of the batch processor. Every line here is intentional. Let us walk through the key patterns. Set EO pipe fail on the first line is not optional. The E flag causes the script to exit on any command that returns a non-zero exit code. The U flag treats unset variables as errors. This catches the subtle bug where a variable name has a typo and silently expands to empty. The O pipe fail flag causes a pipeline to return the exit code of the last command that failed, not the last command. Together, these 3 flags make failures visible rather than silent. Exec2 greater than process substitution duplicates stderr to both a log file and the terminal simultaneously. This means every error from every tool in the script is preserved in type_hints.errors for post-run analysis, while still being visible in real time when you are watching the job run. The is_processed function performs a SHA-256 lookup in the state JSON. If the current file hash matches the stored hash, the function returns 0, the if condition is true, and we skip with continue. This skips the entire Claude API call 0 tokens consumed. The if not Claude-P pattern is critical. We negate the exit code so that failure enters the then branch. The $2> file.error redirect captures Claude's error message separately from the typed output, so an error message is never written into your Python file. py_compile is the safety gate. Claude can generate syntactically invalid Python, especially for complex generic types. This catches it before the file is committed. Only after both Claude and py_compile succeed do we call update_state and mv. This guarantees the state file is never marked complete for a file that has broken output. The most common real-world issue is the py_compile gate catching hallucinated type annotations. Running py_compile catches these instantly, before they reach your repository. Let us look at the token budget and batching strategy that prevents context window overflow. How to keep Claude within context limits and avoid quota-exceeded failures mid-batch. Context window overflow is the failure mode that is hardest to detect, because Claude does not loudly tell you that it truncated your input. The output just looks slightly shorter than expected, and the first several files in the batch have fewer type hints than the later ones. The naive approach concatenates all Python files into one string and sends it as a single Claude-P call. A medium-sized codebase of 50 files with an average of 200 lines, each produces approximately 75,000 to 100,000 tokens in a single request. This either hits the model's input limit outright or forces Claude to silently truncate the earliest files, which you will not notice until you compare the first 10 files against the last 10. The smart approach processes a fixed batch of 5 files per call. Before each batch, it queries Claude/status and parses the token usage. If usage is above 80% of the model's limit, it stops and prints a clear message. Budget exceeded. Resume in a new session. This is intentional. It leaves headroom for Claude's reply tokens and for the next session's system prompt. The WCW trick for token estimation is a useful heuristic. Count the words in a file, divide by 0.75, and you have an order of magnitude token count. It overestimates slightly for code, which is fine. You want to err on the side of underutilizing your budget rather than hitting the limit mid-batch. The batch_size equals 5 constant is configurable. For files with dense type annotations, you might drop it to 3. For small utility files, you can go up to 10. The key is that the constant exists and is documented in CLAUDE.md, so Claude knows the expected scope of each call. What are the trade-offs of a very small batch size, like 1 file at a time? More API calls, higher latency per batch, but 0 risk of overflow and easier parallelization. For most codebases, 5 is the sweet spot. Let us look at the production metrics that tell you whether this system is healthy when running in CI, what to track, and what tells you the system is broken before it causes damage. Building the system is only half the job. The other half is knowing when it is working correctly and, more importantly, knowing when it is not. 4 metrics tell you almost everything you need to know about the health of the batch processor. Tokens per file should stay below 2,000. If you are seeing 5,000 or 10,000 tokens per file, it usually means you are loading Claude.md into every single file call without batching. Or your Claude.md has grown bloated with verbose instructions that are being included in the system prompt on every invocation. Exit code rate should be under 5%. In a healthy run against a stable codebase, these non-zero exits should be concentrated in files with unusual syntax or import patterns. If you see more than 10% failures consistently, stop. You have a systemic issue, not isolated edge cases. Idempotency should be 100%. Run the batch processor twice on the same commit. The second run should produce 0 Claude API calls and 0 file modifications. If it produces even 1, your state tracking has a bug. This is your correctness invariant. If it breaks, everything else is unreliable. P95 latency per file should stay under 30 seconds. A creeping P95, say 8 seconds one week, 15 seconds the next, is often the first sign of quota throttling. Claude is taking longer to respond because it is being rate limited, but not quite enough to trigger a non-zero exit. The failure signals table is your incident playbook. When more than 10% of files exit non-zero, stop the batch, rerun Claude login, and check your quota dashboard. When a second pass generates a different diff from the first, your state file logic is broken. Revert and add a unit test for is _processed. When you see Python syntax errors in the output, Claude is hallucinating invalid type expressions. Tighten the Claude.md conventions and retry. When the state file exceeds 10 megabytes, implement rolling archives that purge entries older than 90 days. Now let us see how this entire system gets packaged into a GitHub Actions workflow for fully automated weekly execution. github/workflows/batch-type-hints.yml. The GitHub Actions workflow is what transforms our batch processor from a script you run manually into infrastructure. You configure it once and it runs itself every week. The cron trigger 02**MON fires at 2 a.m. Coordinated Universal Time every Monday. This is intentional. Low traffic hours reduce the chance of API rate limiting from competing workloads in your organization. You can also add push triggers or pull request triggers to run the processor whenever new Python files are added to the repository. The Claude login step authenticates using a session token stored in GitHub Secrets. This is the same token you use locally when you run Claude login interactively, but here it is passed via the token flag for non-interactive environments. Never hardcode this token or commit it to source control. GitHub Secrets encrypts it and injects it at runtime. The batch processor step runs the full script. Because the state file is committed to the repository as part of the previous run, it is available in the checkout. This is what makes idempotency carry across CI runs. The conditional commit step is elegant. If git diff produces no output, there are no changes to commit, and we skip the commit and push. This prevents your commit history from filling up with empty chore commits every Monday when the codebase has not changed. In a real team environment, you would add a pull request target trigger so that any PR adding new Python files automatically gets type hints added before review. The reviewer sees typed code from the start, without needing to remember to run the script locally. What branch protection rules would you need to update to allow a bot to push directly to main? Most teams use a service account with limited permissions, rather than a developer's personal token. Before we close, let us visualize the state machine that drives the idempotency logic. It makes the overall flow click into place. Every file goes through this decision tree on every run. 0 tokens wasted on duplicates. This state machine makes the processing logic explicit. Every file goes through this exact decision tree on every run. The branching is deterministic, and the outcomes are predictable. Follow the flow from start. The first thing the processor does is compute the SHA-256 hash of the file. It then looks up that hash in the JSON state file. If the hash is present with an exit code of 0, the file is fully processed. We take the yes branch, log a skip message, and move to the next file with 0 API calls consumed. If the hash is not present, or has changed because the developer edited the file, we take the no branch. We load Claude.md into the prompt context to enforce consistent conventions, then invoke Code CLI. The output goes to a temporary file. Before we do anything with that output, we run Python 3-mpy_compile against it. If compilation fails, we log the error and call continue. The script moves to the next file without updating the state file. This means the file will be retried on the next run. Only if py_compile succeeds do we call update_state and commit the typed file over the original. The state file is only ever written in the success path. This is what guarantees idempotency. 3 key insights from this diagram. Cached files consume 0 API calls and 0 tokens. Failures are logged and skipped. The batch continues without stopping. And the state update only happens after both Claude and the syntax check succeed together. The error recovery path, log and continue, is what makes this safe to run in unattended CI. A file that causes a consistent syntax error gets logged every week, but never corrupts the repository. After a few weeks of consistent failures, the error log provides a clear signal to investigate those specific files manually. Let us pull everything together into the 5 key takeaways. What to remember when building headless Claude workflows at scale. 5 principles. These are the decisions that separate a production-grade AI automation from a script that works in demos but breaks in the wild. Principle 1. Idempotency is not optional. This is the foundational invariant. Every other principle builds on it. Hash every file before invoking Claude. If the hash matches the state file, skip. Running the same script twice should consume 0 additional tokens and produce identical output. If you cannot guarantee this, you cannot run the script in unattended CI. Principle 2. Fail loudly, continue gracefully. These might sound contradictory, but they are not. Set UO pipe fail makes every unexpected error visible and terminal. Your script does not silently limp forward on undefined variables. But within the batch loop, continue means a single bad file does not kill the entire job. Fail loudly at the system level. Continue gracefully at the file level. Principle 3. Always validate output. Claude is a probabilistic model. It will occasionally produce code that looks plausible but is syntactically invalid. Python 3-mpy_compile is your last line of defense before that code lands in your repository. Never skip this step. Principle 4. Budget before you batch. Discovering quota limits during a run is the worst possible time. Checking first means you can pause gracefully, communicate clearly, and resume in the next session without wasted work. Always query usage before starting each batch segment. Principle 5. CLAUDE.md is your consistency contract. The state file handles idempotency. CLAUDE.md handles consistency. Without it, Claude makes fresh judgment calls on every file, and the judgment for file the 1st of May contradict the judgment for file 50. Put your Python version, type hint style, and exclusion patterns in Claude.md and update it when conventions change. Teams that internalize these 5 principles build automation that improves over time. The state file accumulates history, the Claude.md gets refined based on failure patterns, and the error log drives targeted improvements to the prompt. Teams that skip them rebuild from scratch after every incident. Let us close with a quick inventory of what you built and what comes next. 4 artifacts came out of this lesson. Batch_type_hints.sh is the main script. Stateful, error resilient, and idempotent. Type_hints.processed is the JSON state file that persists between runs. It is what makes the whole system resumable. Claude.md is the project memory that ensures consistent type hint conventions across every file and every session. And test_batch_processor.sh is the test suite that verifies idempotency and exit code handling. Run it after any change to the main script. Your homework is the most important part of this lesson. Adapting the script to a real project you maintain forces you to make the decisions that matter. Which directories to include, which Python version to target, what type hint conventions your team prefers. The 3 steps are: 1. Adapt the batch processor to a Python project with at least 10 files. 2. Run it twice and verify the second run consumes 0 tokens. 3. Submit the typed branch as a pull request, with Lesson 3.3 noted in the PR body. Lesson 3.4 builds directly on this architecture. It adds error recovery, automatic retry on rate limit failures, and self-healing logic for files that consistently fail py_compile. If you are using this script in CI before completing Lesson 3.4, add a cron alert for when the error log is non-empty after a run. You want to know about persistent failures before they accumulate. Resources are listed on the right side of this slide. The Claude Code CLI documentation is at docs.anthropic.com/claude-code. The PEP 484 type hint specification is at peps.python.org/pep-0484. GitHub Actions documentation is at docs.github.com/actions. And the full course is at systemdrd.com. What is the first Python project you are going to run this on? If you do not have one ready, the sample codebase in the lesson workspace is a great place to verify your setup before applying it to production code. Thank you for watching Lesson 3.3. See you in Lesson 3.4.